What we're going to do now is do a little bit of spring review in preparation for a lab that you're going to do, and also for simple harmonic motion. It's a good idea to make sure that you know your springs pretty well. We had talked about springs a long time ago, back when we were doing energy, so it seems like a good time to review some of the information now. This here is a spring completely at rest. So I've got a mass attached to it, but it hasn't moved anywhere. I haven't stretched it, I haven't compressed it. It's not hanging, it's just resting there. So at this point there's a couple of key features. One is that x is equal to 0. We'll call that x naught. X naught will be equal to 0. The velocity, well, it's also equal to 0 at this time because we haven't done anything yet. So I'm not too worried about the velocity, but it is 0, and then the acceleration is 0. Nothing's happening. I have defined the positive direction is to the right and the negative direction is to the left. Now, one of the things that we can do is we can actually take this and move it off to the side. So let's say that we take this spring and we just stretch it off to the side here. And so now it's at a point which I'll call x max, or A for amplitude. And the direction of its displacement was to the right, so this is positive. So here x is equal to positive A, or positive x max, depending on how you want to do it. Now, one of the things that we learned previously was that when we stretch a spring, the spring will apply a force in opposition to that. So we'll have a spring force that's going in the opposite direction. And the thing that we'll find is that our acceleration is actually be at a max here, because this is the greatest the force is going to be. On the other hand, when we go off to the other side, so now it's swung back and it's overshot the middle, which is the typical behavior of a simple harmonic oscillator. It overshoots the middle and it goes over to the other side to negative A. So we now have x, over here we have x equals negative A, or negative x max. And at this point, the spring force will be equally large, but in the opposite direction. So our spring force will be headed this way instead. I've drawn another picture down here just to illustrate. When we haven't pushed it so far off to the side, the spring force won't be as great. And this relationship between the amount of displacement and the size of the force that results, and also the direction, this was called Hooke's law. So I'll rewrite it here. Hooke's law, and I believe you guys discovered this on your own, but I'll restate it here for you in case you've forgotten how or what you did. So the force of the spring is a vector and the x is a vector. The k is the constant. This is the springiness. The springiness of the spring. And the negative sign indicates that if we move the spring off to one side, the spring force will go in the opposite direction. So let's do just a quick little example. Let's say that we have, actually let me just fill this one out. I'll say that this is negative 1/2 A. So it's half of the maximum amplitude. And let's look at a case where I'm going to give you a spring constant of 40 newtons per meter. So the spring constant is how springy it is, and for me springiness means, I'll rewrite this down here, tendency to resume previous or sort of rest state. So an example of something that's springy that would have a high K value would be steel. And that's one of the reasons why you see our springs made out of steel. Something that would not make a very good spring, would not be very springy at all, would be silly putty, or putty in general, or modeling clay. It tends to just deform. So this, you can hopefully see some correlation between the idea of springiness and what you guys were doing with momentum and elasticity and that type of a thing. So let's just say that we have a spring constant of 40 newtons per meter. And I'll give us that this A is equal to 0.2 meters. So then when we look at this, one of the things that we'll find is that when I go and apply the equation, and I say, what is that force of the spring? We do the opposite of k times x. I have to put in negative 40 newtons per meter times negative 1/5 of a meter. 0.2 meters, 1/5, same thing. And this is all negative of this. So we get a force exerted by the spring of negative 8 newtons. If I do it for this one, it would be the same, only half as large. So I'd have negative 4 newtons. If I did it for this one up here, I'd have positive 8 newtons. And if I, of course, do it for this one here, I get 0 newtons. Okay? So the idea is that the force will always be in opposition. Actually, I screwed this up. I don't know what I was thinking. If I have a negative times a negative, I get a positive. And that meshes with the arrows that I drew earlier. If this one's going off to the left, it's negative, which I correctly put in there. But this one is, of course, going to be in the positive direction. The mathematics confirms it as well, so I get positive 8 newtons as the direction of the spring force when it's compressed in negative 0.2 meters. When it's compressed in negative 0.1 meters, we get positive 4 newtons. So it's not pushing us strongly. It's not deformed as much, so it doesn't have to push us hard to try to get back to its equilibrium state. And then you can see the sort of opposition result up here. So this is the basics with springs. Hopefully you remembered Hooke's law at least a little bit. This idea, this negative sign here, might have seemed kind of insignificant at the time. It's actually fundamentally important to simple harmonic motion, which we'll get into a little bit later. The last thing that I want to do is just go through the idea of spring potential energy. Okay, what we're going to do here is look at the spring potential energy, and this is the force that you're exerting to the spring. So if I just draw a quick little, I'm not sure what happened there, quick little spring setup. And let's say that this is the rest state, and then we move it off to the side a little bit. Actually, that was a terrible job moving it off to the side. Let me give that another shot. There we go. So now we've moved it off to the side, a distance x. In order to do this, granted the spring force is going to be back this way, right? So the spring force will be in opposition to that. But we had to apply a force to it to get it to move away from there. Otherwise, it wouldn't have moved off. So we have to be applying a force to the mass to get it to move off to the side. And that's the force that we're going to be looking at here for now. We're going to look and see how much work did we have to do. Well, the thing is, if we just want to do the minimum amount of work, if we want to apply the minimum amount of force necessary, we can start off with a really small amount, actually. To get it to move when it's not displaced at all, actually doesn't take any force, really. I mean, there's no spring force here. So we just need to apply the slightest bit more than zero force to get it to move. As we continue to stretch it further, it becomes harder and harder. So to get it stretched to this point, we need to apply a larger force. And to get it stretched to here, we need to apply a larger force. And so on. And so we get this trend. And this isn't a... Can't quite get it to match the dots, so we'll go with this one. I can't... we can't forget that Hooke's law is in play. So we're trying to completely counteract the spring force. So one of the things that we notice is that we apply a larger and larger force as we get it to stretch further and further. That's necessary because the spring force is getting larger and larger and larger. Well, what we're going to look at here is work. So how much work did we do? And typically what we've done to find out how much work we do is we take the force and we multiply it by the displacement. But this only works perfectly when you're dealing with a constant force. So if our force is constantly changing, this doesn't quite work out. So what we do is we fall back on the idea of taking the area under the curve. So if I just want to find out how much work is done to move it to this particular point, I just find the area under that curve. If I want to do it for here, I find the area under this full curve. Okay, so we just do the area under the curve, and the area under the curve happens to be a triangle. So we just have to do 1/2 of the force, where I'll treat this as my force. If I want to find out how much work is done to get it to go to this x, all I need to do is get the area from there to there, and it's going to be 1/2 of F times x. And we can find that a spring, in the process of stretching it like this, the spring would do the opposite of 1/2 F of x, or in other words, the opposite of 1/2 times the force of the spring times x, because they're in opposition to each other. And this also works out to be 1/2 kx squared, where the negative sign goes away because we have this negative right there as well. So the work done by the spring in terms of the magnitude of it could be actually 1/2 kx squared, and I should actually put the negative in there just so that we understand that we're losing energy in that sense. But the spring potential energy will be 1/2 kx squared. So when we move it off to the side, we're storing energy as the spring potential. This can be a useful way to help us analyze simple harmonic motion as well, looking at it in terms of energy, but that's not going to be your primary focus. I just wanted to make sure that you have a reminder of how energy and how work works with springs. So the next video will be the last video of the day, and what we're going to do in that video is look into doing a lab using interactive physics. Since I'm not there, we're not going to really do physical labs too much, but we should be able to get through with interactive physics.